Before I jump into just showing you widgets and things, turning on and off, I want to kind of give you an overview of what Rampart is and what it's trying to do so that you can kind of ground the discussion to follow. So really, Rampart is a technology that identifies unusual behaviors in your apps when they're deployed in a production environment. And we define unusual somewhat loosely. It's just something that you see in production that you haven't seen previously in your test environment. So with that in mind, there's really three steps in using Rampart. It's not as simple as just turning on a light switch, of course, right? Like you have to get our agent to attach to your application. That typically involves a few lines of configuration change inside of your Docker container or inside of the script that launches your app. But you don't have to change any of your code. Once our agent has attached to your application, you get an initial assessment of what's happening inside of the app. And we do this using instrumentation. So we go in and kind of like figure out what the app is doing, what kind of code regions it's hitting, what libraries it has, what interactions it's making with the host that it's running on, etc. And then there's this more rigorous workflow that you can enter, which we call training. And during training, we compute this structure that we call a minimum safe behavior envelope. This kind of gets at the notion that Sam was talking about earlier of, what is the least amount of stuff that we need to allow this application to do for it to function correctly in its operationally deployed environment. So during training, you drive the application through its paces in a representative test environment. And that allows Rampart, as it watches the system, to calculate this minimum safe behavior envelope. And then once you've reached a converged behavior model of the application, that means that if you ran your test cases 10 times after convergence, you wouldn't see anything new pop out of it. Once you've got to that converged state, you can ship this thing off into production. And thereafter, you can get alerts and notices and even blocking of especially egregious events that show up in your production environment. And that's the true value of what Rampart provides. It doesn't rely on heuristics. It doesn't rely on anything that's specific to certain attack vectors. The only thing that it's looking at is a delta between what it saw in your training and testing environment and what it's seeing in your production environment. And that turns out to be very valuable and very useful. So to drive that home, we have a demo prepared for you that I'll be going through. And there's a number of different components here. I'm not expecting you to memorize all this. I'm just going to give you an overview so you know what to expect as I move through the pieces. Really, there's two parts to the demo. The first part, we're going to look at Log4Shell, and we're going to do that running inside of a place that I call the Rampart Cyber Test Range. And there are a bunch of other apps in there beyond Log4Shell, and hopefully sometime I get a chance to do more of these demos and show more of the apps that we work with. But for now, we're going to focus on Log4Shell first, because it's cool, it's relatively easy to understand, and it's truly horrible in its implications for security. So what we've done is we've deployed two different versions of a Log4Shell proof of concept application inside of our cyber range. One of them we're calling Log4Shell Red, and one of them that we're calling Log4Shell Green. They are the exact same application. They're running as Docker containers, so the jar that they're mounting is exactly the same. They're running on the same base image, but they are two distinct containers. And the only difference between them is that the green endpoint has our Rampart agent attached to it, and it has a converged behavior model associated with, with the way that this proof of concept web service is supposed to behave. So we're kind of starting at step 3 in that workflow that I showed you before. So we're going to focus on effect-oriented stuff in this demo. And again, hopefully in the future, I get a chance to either in blog form or live demo show what it takes to get our agent attached and what it takes to do that training process. But that's a completely different discussion from what we're showing today, which is once you have Rampart protecting your application, what is it you see and what is the benefit of getting to that point? There will be some stuff that runs on my laptop. I'm going to interact with a browser-based interface into the cyber test range so that I can get access to these services that are running inside of a Docker Compose, essentially. I'll be using a management client to interact with what we call the Rampart Polyglot server, which is essentially the server-side control component that tells these agents how to behave, what they should be looking at, what they should be blocking, what they should be allowing, etc. And I'll show you how we can do really interesting things dynamically with that interface. And then, of course, there's the SIM, right? That's the other component here that I haven't talked about yet. And in this demo, the SIM is just an Elasticsearch instance with Kibana sitting on top of it. So it's a pretty simplistic setup. But you can imagine this is something involving Splunk or whatever your SIM stack of choice is. We have ways of hooking into it. And we've got integration pathways with a number of different ones. But today we're going to focus on Elasticsearch and Kibana. And then also on my laptop is the second demo. This is one that is, I think, the cool one, which is Doom. So we're going to show you a fork of the Doom code base that our agent's going to attach to that has some really nasty stuff inside of it. And I'll show you how we can trigger that and what our agent does when it detects it and picks it up. So let's move on to the actual meat here. So give me 1 second. All right, so this is the sim. And Daphne, can you just confirm that you're seeing this before I model?
Yes.
Okay, great. So as bad stuff happens in the next few moments, you're going to see events and telemetry pop up into this view. So for now, there's not much here. It just says that it's monitoring a certain number of hosts. In this case, it's only monitoring one host, and there's one active context. That means there's one application running, and we're monitoring its behavior continuously. And this is all running inside of the cyber range, kind of like the architecture that I just showed you on the PowerPoint slide. Now, the next thing that I have here, this is actually a website hosted within our cyber range. And this is essentially an attacker playbook that operators can use to go through and basically follow instructions, kind of like a guided hack the box tutorial type of a thing, where you can follow instructions to actually break into an endpoint. So what I'm going to do is I'm going to be copying and pasting snippets of code, snippets of scripts into this interface here, which is just a bunch of browser shells that are one way of interacting with our cyber test range. Now, there's other ways of interacting with it. For example, we have a VPN ingress option. This is kind of like the noob interface, though, and it's easier to use and more reliable. So I'm just going to hit it this way. But if you're imagining, like, how would I use my own tools or my own, custom setup, that's very much something that we've accounted for, and it is a possibility. So what I'm going to do is I'm just going to follow along as we break into a basically a web service that has a vulnerable version of Log4j inside of it that is susceptible to that horrible Log4Shell exploit that we heard about round about a year ago, back in early December. So there's really 3 steps to the attack. The first one is the easiest. It's the bad guy opening up something that's going to listen to incoming requests. So right now we're just going to use netcat LNVP on port 1234. And what I've done is I've set a timeout of 2 minutes so that this shell will die after 2 minutes. And I'm doing that so that I can reuse it to attack try to attack the green endpoint after I attack the red one. So what I'm going to do first is attack the red endpoint, and I'll show you that it's it's very, very susceptible to this attack. And then I'll try to hit the green one in just a moment, and you'll see that it's definitely not. So I'm going to start up the netcat listener, and now it's the bad guys listening on port 1234 for some kind of an incoming connection. The next thing the bad guy is going to do is start up an evil LDAP server endpoint. Okay, and this one's interesting, but it's critical to the way the exploit works. Really what this does is it serves up a malicious Java code object called export object. It's just a serialized object that's served over the wire. And what we have to do is trick this version of Log4j into reaching out over JNDI to this endpoint where this malicious object will be served up to it. And then once that client, aka the target app we're trying to attack, tries to deserialize that object, that's when the bad stuff happens. So it's going to run this nc command and pipe it into bin.sh. So it's basically going to give us a shell that we can use to exploit the system. And exploiting it is trivial. This is what made this attack uniquely awful. All you have to do is issue some kind of a request to the server that winds up being logged. And in this case, the request being logged just has to have this weird looking JNDI LDAP URL looking thing in front of it. But it's just a header, right? This is a key value pair that the server happens to be logging, just doing some low level logging stuff. So as far as we're concerned, the service endpoint worked correctly. It's a really simple REST API. In this case, just saying hello world. Again, it's a proof of concept. But if I go back to my bad guy shell, which is terminal 1, I just got a connection on this box. Who am I? Of course, this is a demo, so this is root. You could imagine in the real world you're not root, but either way, you have a foothold on this system. What I'm doing now is I'm catting out a flag file. And if you're familiar with Hack the Box or similar environments like that, there are essentially secret files. And by virtue of reading those secret files, you demonstrate that you've been able to compromise the system. So my shell just timed out there, but that's okay because I was able to capture the flag in that amount of time. So what I can do is I can capture, and then I'm just going to paste this random string, which turns out to just be some UUIDs that are appended together. And I have captured 1 out of the 23 flags in this cyber range. Like I said, we have tons of apps, and we're only looking at a few of them in this demo. So what that means is that the red endpoint was trivially exploitable, right? With a very small number of steps, I didn't have to customize anything, worked on the very first try. I was able to hose that endpoint, no problem. So now what I'm going to do is I'm going to run the second part of this attack. And again, there's no telemetry happening yet because I've only hit the vulnerable red endpoint. But now I'm going to do something different. I'm going to try to hit the green endpoint, which has our Rampart agent attached to it. So I'm going to do the exact same command. I'm just pressing up to get back in my history. NCLNVP on port 1234. Now I'm listening again. I'm going to fire up the exact same evil LDAP server as before. Nothing has changed there. And it's ready to serve my malicious export object on request. The only thing that changes in this demo, or at least in this part of the demo, is the endpoint that I'm making the request to. I'm replacing the red endpoint with the green endpoint, and this is the one that has our agent attached to it. So I go over here and fire off the request, and boom, I get back hello world just like before. So it's not immediately obvious that anything interesting or noteworthy has happened here. I also, if I go over here, I see that just like before, this export object class is being served up to the target application, which is interesting considering the fact that there's no incoming shell connection from the target machine back to my bad guy listen port. So the attacker, sometime between when that serialized object was served to the target app and when it ordinarily would have done the runtime exec that hosed the box, Rampart interceded itself into the execution flow of that application and prevented the bad thing from happening. So let's go and look at the telemetry view of this just to kind of show you what happened here. So there's a number of different things that have changed here. We see a breakdown of the events that Rampart just saw by their degree of severity. So there's a relatively large number of low severity events. And these are things that are caused by unusual execution of control flow, but nothing that's truly terrible or considered significantly divergent from normal application behavior. We see some medium severity stuff related to networking, and these events are related to the outreach to those 2 ports, like the JNDI LDAP ports that were used by the attacker to serve up that bad object. But what's really interesting here is this guy right here. So what I'm going to do is I'm going to apply a filter to get a view at just this one event and give you some insight into the kind of telemetry that Rampart produces. So first of all, this is a very severe thing. This one showed up as the highest level of severity that Rampart knows about. The corrective action taken was block, whereas with all the other events, the corrective action taken was just to alert on it. And the reason for that is we have a policy in place that says that whenever we reach a region of code that's trying to do a check exec, in other words, trying to spawn a subprocess, we should be very skeptical of that and block it if it's something that we haven't seen before in the trained application. So indeed, here we see exactly that. It's trying to run binsh, and there's a string associated with that binsh that's actually the command being run. Rampart does see that command, but it's only reporting here the fact that binsh is the executable running. And if we check out the full stack trace here, which again is not perhaps initially as interesting as the fact that something bad has happened related to code execution, but it is very interesting if you start looking into forensic analysis of what actually happened. And just like I said before, check this out. On one of the upper stack frames here, I see this export object thing, and I see init. And in Java, init is the like secret name that the Java compiler gives to constructors. So what's happening is that inside of the constructor of this malicious object that got served up to the target app via JNDI and LDAP, inside of the constructor is where this runtime.exec call happens. And that's what triggers this process builder start, which is what Rampart hooked into and said, hey, that's not something the app normally does. So I'm going to go ahead and block it because it's really sketchy. So that's a great example of the kind of thing that Rampart can save you from even without knowing about it ahead of time. When Log4Shell came out, again, back in early December, within 3 or 4 days, we had a proof of concept up and running, and Rampart blocked it out of the box the very first time we tried it. We didn't have to do any custom tailoring or anything like that to put in special heuristics. Just by virtue of seeing that there's a delta in application behavior, it was enough to catch this thing and stop it dead in its tracks. So what I'm going to do is purge out some of these filters, and I'm going to move on to the Doom demo here, which is one that's very near and dear to my heart, and also seasonally appropriate, sort of, since we're going into Halloween season here. So what I did was I found a port of the Doom code base, which was, many years ago, released as open source. And so what I did was I found a port of that into Java. So some enterprising group of individuals put in the work to translate some C code into a form that runs and just entirely in Java. So what I'm gonna do is I'm gonna start up this version of Doom called Mocha Doom. Mocha obviously having the coffee connotation in Java. And I'm gonna start this thing up. Oh, I only want to start one of these. And what we're seeing here is the splash of our application as it boots. And this is something that, you would see some of this on the default application when it loads, but a lot of it is unique to the fact that Rampart is booting the application. So keep your eyes on the right-hand portion of the screen here, where those, like the colored bars associated with severity will appear. And I can try to move this console a little bit out of the way so we're not looking at that too much. All right, so try to keep your eyes on this upper right portion of the screen as I interact with the game. So what's cool is that out of the box, I mean, who would have thought that this kind of tool would work on something like Doom without a significant amount of work, without doing a lot of code changes. In fact, we had to change none of the Doom code to get this to work. We just dropped our agent jar in there, and it's now talking to our Rampart polyglot server. And like I said, I already have a fully converged model of how Doom is supposed to behave. So I can go through the game. Everything is fully functional, including the sound, even though you're not hearing it. It's a little bit overwhelming hearing all the zombie noises and stuff when I'm trying to talk. So I can go through the game. I can kind of like speed run the first level a little bit. And hopefully at least some of the people on the call play this game before. It's pretty old school, but it is one of the classic games. So that's all well and good. The next question is, what can I do in this application that would demonstrate the value of Rampart to detect unusual sequences of control flow or unusual interactions with the host system? And one thing that popped right into my mind, because I played this game as a kid, and I remember doing this as a kid, is cheat codes, right? In the original game, there was a function where you can type in strings, like a special string on your keyboard, and it will do certain things that make the game easier to play. Like it will turn on God mode, which makes you invulnerable, or let you walk through walls if you're stuck somewhere, or you can give yourself all the keys and ammo, and that makes it really easy to progress through the level, and without really actually needing to go through the tediousness of making your way through the maze part of the game. So what I'm going to do is I'm going to type in IDKFA. That's the cheat code to give myself keys and full ammo in Doom. So I'm on my keyboard right now. There's no terminal or any magic like that. I'm just typing IDKFA. Here I go, IDKFA. So I typed in that code, and you'll notice that a number of things have changed in my heads-up display. Like now I have this awesome 1992 grade rocket launcher thing, and I can bust up guys a lot better than I could with my weak gun that I had before. And what you see is right away, like within a matter of seconds, Rampart telling us that something sketchy has happened inside of the application. Now, these are all relatively low severity events, which means that Rampart saw them as odd, but they were close enough to normal execution that it didn't think they were worth blocking. And in fact, all of them show up as alert. So if I go down here and look at the telemetry, and I'm just going to kind of look for a magic string, I already know where the code is implemented. But one of these alerts that's generated tells you exactly where the cheat codes are implemented. So it's this basic block, a sequence of instructions inside of the check cheat method in this m checks cheat sec t module inside of the Java code base. So that tells you exactly where in the code that the app has gone off the rails right now. So that's cool, right? Like we can tell when the app does something unexpected, and it works on Doom. But I wanted to make it even more interesting than that. So what I did was I put in another cheat code that didn't exist in the original source code. Again, this is open source, so it's pretty easy to go in and just muck about with the code to do something terrible that it wouldn't originally have done. So I added a new code, and it's ID pwned. And when I type in ID pwned, it's going to do a number of terrible things on my system. Not all of them will actually activate, but what we're going to do is look at the telemetry and see if we can reverse engineer what goes wrong. So ID pwned. And I do see some red text up at the top there. Like that string is definitely not something that shows up in the original game. And I'll do it one more time. That red message that showed up at the top, that's definitely not something that ever shows up anywhere in the original Doom code base. What we'll see is in a number of seconds, Rampart's going to report on some really sketchy behaviors inside the application. And indeed, there he goes. The Rampart is telling us, I ran it twice, so there's two like blips of telemetry associated with this. It's telling us that there's some weird threading stuff happening. In other words, somewhere in the code, a new thread is being spawned, and that hasn't happened before. And there's also a whole bunch of new code units associated with the backdoor that I put in that we haven't seen before. So let's click on the execs, the highest severity ones. I'm going to apply a filter on this guy. Scroll down here, and let's look at what we see. So I see a check exec command calc.exe. And this is one that has an action of block. So Rampart blocked calc.exe from running. It also blocked cmd.exe from running, which is weird, right? But what my backdoor did was it tries to run a reverse shell using a pure Java methodology. So in other words, it's kind of like building netcat in Java in the source code itself. It tries to phone that reverse shell home to the attacker box, which you can't reach because you have to be on the VPN to do that, the CTF range VPN. But what's interesting here is we see the stack trace where this occurred. So this is happening inside of a status bar lambda, inside of status bar.java line 880. And if I go to the diff, the GitHub diff of the code base, so here's status bar.java. There's only a small number of changes needed to make this happen. Let's look at line 880. Check this guy out. This is a very well-known one-liner for basically building a shell into Java code. And that's what Rampart picked up on without knowing anything else about the app ahead of time, without doing any kind of heuristic analysis or signature analysis, just because it never saw this code region get hit before, and it's doing something really sketchy. And we also see this, it's reading some environment variables here to find out where it should be phoning that shell home to. But what's really cool about this is I can go in through a dynamic management profile that's attached to this agent right now without rebooting it. And I can say, well, maybe that's okay to run. And again, you would never do this in a real production environment. Like there's no reason you would ever allow a suspicious check exec to happen. But just for S's and G's, let's fire this off. I'm going to commit this as a behavior override. It takes a couple of seconds to propagate to the app itself. But without rebooting the application, I'm able to enact changes to the security policy. And typically you would do this if you have false positives. That would be when this kind of thing becomes useful. Like if something is generating a lot of alerts, you don't want it to, you can do this as a way of filtering those alerts out. But at any rate, I added it here. So now I'm going to do ID pwned again. Type in ID pwned and check that out. Calc.exe just spawned. And it's also spawning, it's trying to spawn that shell in the background, even though it's not able to reach the endpoint. So without us knowing that this was even embedded inside the application, Rampart previously protected us from it. And again, that's a great example of in a legacy system, but you could use your imagination how that very much applies to things like web services and stuff that we use today. How Rampart can protect you from things simply by virtue of looking for unusual or unexpected events that occur at runtime.